My name is Pranay, and this is the MBTA visualization project. So, this project has been an incredible learning experience. We learned tons of information about cloud computing, how to make projects scalable, and how enterprise projects work. Our main problem statement for this project is that when a user is at a train station, we need to tell him when the next train will come. Maybe he's at the train station right now, or he's going to be there later. But he can log into our application and find out how long he has to wait for that next train to come. So when we first started out with this project, we compacted everything into one server, which is when our mentor stepped in and told us that's not a very wise thing to do because it's not scalable. So we thought about it and we ended up with a current architecture which looks like this. So as you can see, it's pretty scalable and it's divided into different units. Each different unit exposes an API through which it communicates. Um, so it's scalability is the main focus here. How this works is the user puts in his request to the UI. The UI collects data such as the start stop, end stop, etc., etc. It makes a GET request with this information to the front end server, which packages this information and makes an API call to the backend server. The backend server then queries this call and makes a query to the DynamoDB data store, which returns back with the information for that stop. The backend server then compacts that information into a JSON file and responds with that JSON file. The front-end server then parses that JSON object and passes that information to the UI, which then displays it to the user. So as you can see, it's a very elegant solution for this problem. Um, the UI is written in Bootstrap, CSS, and HTML. The front-end server is written in Node.js and AngularJS. The backend server is written using the Jersey framework for Java. We use DynamoDB data store, and the data pipeline is used to query the MBTA API, get the information, and store it into the database. So we run the data pipeline in regular intervals, so our database is always up to date with the latest train informations. We'll have Alex talk about the front end server, then Siwan will talk about the back end part, and then Andy will talk about the data pipeline and some of the algorithms we used for this project. Enjoy.
You see that we have a beautiful UI. So the top left, you see our custom logo. And then right here, Boston Now is the name of our application. It is a free MBTA prediction service. So we offer two services. If you want to go somewhere now, how long you want to know how long you want to wait for the MBTA, and if you want to go somewhere later, and when exactly would the train get you. So let's say if you want to go somewhere now, we'll test it out the system. So first, you get asked for the color of the T that you want to write. Say you want to choose the red line or the green line. So if you choose the green line, then it asks you for which line you want to write: the B line, the C line, the D line, or the E line. So you choose the C line, or choose the C line. Direction travel, inbound, and then you select the starting stop that's populated based on these selections. So the stop selection is populated differently if you choose the beat line or the D line or the E line. So if you choose beat line and then you also want to go inbound, then you see that a different set of stops are populated. Boston University West, you want to go from there. And do you want to transfer lines? That means would it happen that you might start on the green line and then end up on the red line? So if you say no, then you simply choose from the same selection as right here. So you say you want to go to Boylston, and then you go to see results, and then go over here. You see that API calls are just made to the server, the backend server, and the results are popping up. And then come down here, the results are shown right here. So the green line right now is experiencing minor delays due to an earlier police action at Park Street. And the next coming green B line, the B train will arrive in 60 seconds at Boston University West. And then sometimes we'll give you more details to the alert, in which case you can click on this button and see more details. So yeah, so if you say, let's try out a different line. So if you want to go to the blue line, and then you see that the blue line map pops up. This helps with the visual. You want to go outbound, and you select. You want to go to. You want to start from the airport. You want to try to get somewhere, and you want to end up at. You want to end up at State Street. So you go to see results, and then come down here. The API calls are being made to the backend, and then come back here. The results are shown. Blue line is currently experiencing minor delays due to a disabled train at Wonderland Station. So the train will actually get there in 5 minutes and 17 seconds. Now, let's say if you want to switch lines in the middle. So a common stop that people might do is if you want to go from the airport to and you want to switch lines and maybe come back to Boston University. So in which case you want to say yes, and then you choose the green line, and then say the beat line, because BU is on the beat line. You choose the direction of travel, you're going outbound. You want to select the stop, Boston University East. Go to see results. The API calls are just made. The results are popping up. And then it tells you that yes, you could do this, and the actual blue line will be coming in 4 minutes and 28 seconds. So everything with service 1 works perfectly fine. And then let's try out service 2. Is if you want to go somewhere later, and you want to know when will the T get you. So our application asks you for where do you want to go. So you choose a time of day. Say you want to go in the morning, and then time closest to your travel. We're doing 30-minute intervals. So let's say you're going around 5:30. So you choose 5:30 a.m. and then same things. These fields don't change. And then, or if you want to change them for the sake of the demo, we'll choose the red line, and then we just want to select a stop. So you want to go to MIT, go for MIT to BU. And you go to see results. Again, the API calls are being made. The results are coming back to us. And then sometimes this could be a little slow because the backend algorithm is a little glitchy. I think the backend team is still working on that. So anyways, we'll come down here and we'll see the results are shown. That it tells us that the red line is experiencing moderate delays due to a disabled train at Charles. And the train, so therefore it will actually get to us. There will be one train at 5:32 a.m. because we selected 5:30 right here. Now if we choose a different time, let's say we want to choose 6:30 a.m. then in which case we should get, let's see, okay, so the API calls are being made. It tells us again that there's the disabled train, and now it tells us that there will be a train at 6:30. So another really cool feature that works perfectly is the bookmarkable URL, which basically means that the URL is dynamic based on the user selections, and this means that the user can simply save the URL and then paste it into the browser, reload the page, and then all the fields should be already populated. Yeah, so all the fields are already here, so all they have to do is click see results, and then the API calls are being made and the results are coming back to us. So this is very convenient for the users. This also means that the user will be able to change anything in the URL and then get the results that they want. Say if they want to choose, instead of red line, see if they want to go to blue line. And then we'll just, instead of going outbound, we want to go inbound. So we try that out, refresh the application, come down here, we see that blue line is automatically populated, the direction has been changed to inbound, and all we have to do is choose a stop. I want to choose choose this stop. Will you transfer lines? Yes. These things are the same. See results, and then the results are coming back to us, and then it tells us exactly what's going on with the blue line, and that the blue line train is right here already. it'll be arriving in 1 second.
Hi, this is Siwan. I will talk about RESTful API, the use of different Amazon Web Services in our project and database design. So I work with Pranay on our RESTful API, and I work with Andy on the data pipeline. Basically, a RESTful API is an application program interface that uses HTTP requests to get, put, post, and delete data. It also interfaces with external systems as web resources identified by uniform resource identifiers. For our project, the front end only uses GET requests to require information from backend server. Casella stands for Java API for RESTful Web Services. We chose to use Jersey, which is an open source framework for developing RESTful Web Services in Java. Jersey libraries are supported by Maven framework, so by creating a Maven project in Eclipse IDE, we can use the Jersey library that help us to build the API and run on Tomcat server. There are two main parts of our RESTful API. The first one is that we use the part of URL as the path to different services. And the second one is that we use the path parameter to query our database. In the first file, firstly, we use the start ID and end ID to do a graph search. If the user needs transformation, we will provide the shortest path to them. And then we will use line color to find corresponding table in our database and use the start, stop, and time to do the query. This code also shows us how to use the key value feature of DynamoDB to query the database. So for Amazon Web Services, we use Elastic Beanstalk to run and manage RESTful API in order to talk to front-end server. In this way, RESTful API plays a role like an intermediate agent. The front-end only needs to put the user's request in a URL and get a result from our RESTful backend server. For time prediction services, we require line color and start ID and end ID to predict the specific time within an hour. And for time prediction over an hour, we need the user to provide time to us, and then we can provide the corresponding data. And for alert header and detail, this is the URL that we query the database. DynamoDB is a NoSQL database to store the MBTA data. It's very useful to deal with the condition that needs a lot of query operations, since the primary key in DynamoDB is stored as a hash value, so we can retrieve the data we need in constant time. So firstly, we use the data pipeline to create useful table, and then there are four important table that we use to communicate with the RESTful API directly. For alerts, there are two important tables. The first one is alert headers, and the other one is alert detail. This is how the table looks like, and the stop IDs are the primary key for both tables. And for prediction, we have prediction by route and prediction by stop. Prediction by route, it provides real-time prediction within an hour, and we update the prediction for the nearest coming train every minute. And for prediction by stop, it stores the historical data of the past days, and then we calculate the average value and provide the prediction for time over an hour. And then we update the prediction for all the coming train every half an hour. This is the prediction by route and tables. We separate each line into different tables. And this is the prediction by stop tables. And this is how the table looks like. For prediction by stop, pre-array means that at different time there are several trains coming at that time, and the pre-array starts recording the data at 0 o'clock in the morning, and then it stops at after 24 hours, and it records the data every half an hour. And prediction by route is used to provide real-time precise data to the user.
Hello, this is Andy. I'm talking about the data pipeline and path finding algorithm. A data pipeline is a component which extracts the data through the RESTful API of MBTA and write to the Dynamo database. We specify the endpoints we are using, the API key and the query condition, and the return format. The endpoints we are using in our system is routes, stop by routes, alerts by, and also predictions. Using the HTTP component to generate a GET request and GET response. And then we parse the JSON, and as well as we handle errors returned by the MBTA API, such as no data available or invalid query. To write to the Dynamo database, we accessing the service using the AWS SDK, as well as creating tables, and for the items, the create, update, read, delete operations. We're using the DynamoDB mapper class, which can access to the table and allow us to run queries or scans. This is useful for updating and deleting items. So we update the table executed at regular intervals. For example, all stops we run once a week, and predictions every minute. And we deleting all the items stored more than 2 weeks. And for database maintenance, we generate a daily rolling log file, so we know which table is updated and how many items are affected. To reduce the number of API calls, we set the prediction and the alert data thread to sleep during 2 to 5 a.m. Path finding algorithm is a program runs in the backend server, returns a shortest path between the two stops. First, we build the graph data structure, and we use singleton pattern, so this structure is only built once for the server. So each vertex is an MBTA subway stop, and each arc is a route that serves two stops. We're labeling with the route ID, the number, the direction, and the distance. Calling the MBTA routes and the stop by route, and we connect the two stops based on a stop order field, and the stop have the same geological coordinates. So there's total 255 vertices and 644 arcs. We implementing a A-star algorithm with small modifications, and the user take source ID and target ID and how many transfers she will tolerate. So in algorithms, our cost is travel time. We use a heuristic info class to store this additional information. So the algorithm is first we initialize the frontier and explore list, and then we put the starting node on the frontier. We do a loop until the frontier is empty. First, we find the node with least cost, and then check if the cost is greater than the cost of shortest path. We call it T-min. It will return the shortest path because there's no possible you can get faster than that. So then we check if the time cost of the current path plus the time walking to the end is smaller than the T-min. If it's, we update the shortest path and T-min. Then we search for all the neighbors, and we calculate the cost, check whether the next stop has been explored. If so, we update the call. If so, and the cost is smaller, we update the nodes in the explorer list and all the paths that's passing through these stops. If the stop has not been explored, we just update the path and check if the transfer time is okay. We add it to the frontier. Here's the Java class structure for all of this, and a little demo. So we build a graph and run 2 queries. One is from the assembly to Fenway, another is to Wood Island to Harvard. So you can see the first one, we have a shortest path, travel through the orange line to green D line and make transfer at green D at Haymarket. The second one is travel from the blue line and change to green line at Park Street. Also make a transfer to red line to travel to Harvard. So this time we need to make 2 transfer. Yeah, that's all. Thank you.